In 1887, the German physicist Heinrich Hertz was conducting a series of experiments to prove a central theory of electromagnetism. He needed to show that invisible electromagnetic waves were actually traveling through the air. To detect them, he used a simple wire loop with a tiny physical gap between two brass spheres. By applying a high voltage, he created a sensitive receiver for these invisible waves. When the incoming waves hit the loop, they generated a small surge of electricity. This arced across the gap as a faint, crackling purple spark. Hertz was working within the established laws of his time. This setup was intended as a final confirmation of classical electromagnetism, yet it produced an effect those laws could not account for. Because the spark in his detector loop was so dim, it was difficult to see in the laboratory. To help him observe the results, Hertz introduced an arc lamp into the experiment. This lamp cast a strong beam of ultraviolet light directly onto the metal surface of the emitter plate on the loop. The moment that ultraviolet light hit the metal, the electrical discharge changed. The spark across the gap grew white-hot, becoming noticeably thicker and more intense. Hertz verified this immediately. If he placed a glass plate in front of the lamp to block the ultraviolet rays, the spark weakened. When he removed the glass, the surge returned. This created a physical mystery. He had to determine why shining an invisible wavelength of light onto a solid brass plate would alter an electrical current jumping across empty space. To find the answer, we have to leave the 1880s laboratory and zoom deep into the microscopic surface of that metal plate. Inside the metal, a rigid grid of positively charged ions is surrounded by a sea of negatively charged free electrons. These electrons drift around the material, and their movement is what allows the metal to conduct electricity. While these electrons move easily inside the metal, they cannot escape it. Anytime an electron reaches the outer surface, the attractive force of the positive ions pulls it right back inside. This internal barrier is known as the work function. The work function is the specific minimum amount of energy an electron needs to absorb to overcome that inward pull and break free from the surface. Under normal conditions, these electrons lack the necessary energy. They remain trapped at the surface, unable to bridge the gap and help the electrical spark cross the void. But when Hertz turned on the arc lamp, he introduced a new variable. Invisible high-energy ultraviolet radiation crashed into the brass plate. The free electrons sitting near the boundary of the metal physically absorbed the energy from this incoming radiation. Ultraviolet light carries significant energy. The energy delivered to these surface electrons was high enough to exceed the metal's work function threshold. Energized by the light, the electrons bursting away from the surface broke their ionic bonds and were ejected from the metal into the surrounding space. This specific phenomenon, where light physically knocks charged particles out of solid matter, is known as photoelectric emission. By returning to the macro view of Hertz's laboratory, we can finally explain why his spark gap grew so much brighter. Those newly freed electrons cascaded into the void between the two metal points, creating a highly conductive bridge. This cloud of negatively charged particles lowered the electrical resistance. The current took this path, resulting in a much more intense discharge. The ultraviolet light acted as a catalyst. By providing the necessary charged particles to bridge the void, it allowed the high-voltage current to flow more easily. There is a significant historical irony in this experiment. Hertz had documented the behavior of electrons 10 years before the physicist J.J. Thomson would officially identify and name the particle. Hertz could not yet name the particles he was liberating. However, his meticulous records of the specific light frequencies required for the surge provided the data later researchers would use to connect light to the movement of matter. The problem was that the classical wave theory of light could not explain how this happened. According to the rules of the 19th century, this instantaneous emission was physically impossible. That faint spark in a dark laboratory became a foundational observation that the old laws of physics could not resolve. It was this specific contradiction that eventually led Albert Einstein to propose that light travels in distinct packets of energy.